We all picture the periodic table as this perfectly organized chart, right? Everything's sorted into these neat little families. But what if I told you some elements are total rebels? They act way more like their neighbors than their own siblings. Today, we're going to unlock a hidden code in the table, a fascinating exception that actually reveals an even deeper, more beautiful rule.
All right, so here's the plan. First, we're going to look at how these rules get bent in the first place. Then, we'll uncover something called the diagonal connection. That's the key to all this. We'll dive into the science behind it, introduce you to some, let's call them unlikely chemical twins, and finally, we'll see why this weird little pattern actually matters a whole lot.
So let's start with the basics. You probably remember from chemistry class that elements in the same column, they're like a family, right? They've got the same number of electrons on the outside, so they're supposed to act alike. But, just like any family, chemistry has its black sheep.
Okay, let's take a look at lithium. It's sitting right there in group 1, so it should be best buddies with sodium and potassium. But here's the weird part. It acts a lot more like magnesium, which is over in a completely different group. Now, that's not supposed to happen. So what's the deal here?
Well, the answer isn't where you'd expect. It's not found by going up or down the table. Nope, you have to cut across it, diagonally. And this strange, unexpected pattern, it actually has a name.
It's called the diagonal relationship. And listen, this isn't just some random coincidence or a fluke. It's a real, predictable pattern, and it specifically connects elements in the second and third periods of the table. This diagonal line is the hidden logic we've been searching for.
And here they are, the three classic pairs that really show this off. You've got lithium and magnesium, that was our original puzzle. Then there's beryllium and aluminum, and finally, boron and silicon. See that? It's a perfect diagonal line right there on the table.
Okay, so now we know what it is, right? We've given it a name, but the real question, the big one, is why? Why does this happen? Well, it turns out it all comes down to a kind of perfect storm of three key atomic properties.
All right, reason number one, their size. Think about it. As you go down a column, atoms get bigger, but as you go across a row, they actually get smaller. So what happens when you move diagonally? Well, those two effects, one making it bigger, one making it smaller, they practically cancel each other out. It's amazing. And the result is that these diagonal pairs, like our friends lithium and magnesium, end up being almost the exact same size.
Reason number two is a big one. It's called charge density. Now, just imagine you have a tiny little water balloon and a giant one, but you put the same amount of electrical charge into both. Which one has a more powerful, concentrated punch? The tiny one, right? That's charge density. And because our diagonal pairs have a similar size and a similar charge, their charge density ends up being nearly identical. And that is huge, because it means they affect other atoms in almost the exact same way.
And finally, reason number three, their electronegativity is practically the same. That's just a fancy word for how strongly they pull on electrons when they're in a chemical bond. So let's recap. You've got a similar size, a similar charge density, and a similar pull on electrons. That's it. That's the three-part recipe for this special diagonal relationship.
Okay, so that's the theory, that's the science behind it. But does it actually hold up in the real world? In the lab? Let's take a look at the evidence and see just how deep this resemblance between these unlikely chemical twins really goes.
And this is where it gets really cool. Look at lithium and magnesium. Most of lithium's family, the alkali metals, won't touch nitrogen. But lithium, it forms a nitride, no problem, just like magnesium does. Or take beryllium and aluminum. Beryllium's family usually forms basic compounds, but beryllium itself makes what we call amphoteric oxides, which means they can be an acid or a base. And guess who else does that? Aluminum. And of course, boron and silicon, they're both semiconductors, which is literally the foundation of all our modern electronics. See, these aren't just vague similarities. These are very specific shared behaviors that go completely against their family trends.
So at this point, you might be thinking, okay, that's a pretty neat piece of chemistry trivia. And you're right, it is. But this pattern is so much more than just a fun fact or a quirk. Understanding it actually has some pretty big implications for how we predict what elements are going to do.
So, what's the big takeaway here? Well, first, this isn't just about memorizing a few pairs of elements. It's actually a super useful predictive tool for chemists. But I think, more importantly, it shows us that the real rules of chemistry aren't just about simple columns and rows. They're about these fundamental properties: size, charge, and electronegativity. The diagonal relationship doesn't actually break the periodic table's logic. It reveals an even deeper, more elegant layer of order that was there all along.
And that really makes you wonder, doesn't it? I mean, this whole pattern was hiding in plain sight, right there on one of the most famous charts in all of science. It just begs the question, what other beautiful, hidden patterns are out there, just waiting to be discovered in the rules of our universe?